Hello class, time for another lecture on sound isolation. This time we'll be talking about sound transmission class. So here's the definition. First let's go up here, say the STC is the common abbreviation. People just say STC a lot, but it stands for sound transmission class. This is a single number rating used to compare sound insulation of partitions. And this could be any type of partition. It could be walls, floors, ceiling, windows, doors, hatches, anything like that. This STC is primarily it's primarily used in the USA and Canada. Other countries use the weighted sound reduction index, which is the R with a subscript W. It's derived from transmission loss measurements in 16 test bands, so from 125 to 4,000 hertz. There are a couple standards that are followed to measure this. I'll probably post those in supplemental materials so you can see them if you want. Then, last thing, it's weighted for human sensitivity to sound. We'll see that on this slide. So here are the 1/3 octave band transmission loss values that were measured. The way this is measured is you measure the sound pressure level on one side of the room, on one side of the partition. So one room's going to be your source room, one's going to be your receiver room. You produce a lot of noise. So take some high-powered speakers. There's a very specific way that you put them in the room. You play pink noise through them. You generate a lot of noise. You measure on that side, and then you go and measure in the other room. There are other things you need to do too, like you need to measure the amount of absorption in the receiving room so that you can normalize the transmission loss values. If you measure a receiving room with a lot of absorption, you're going to get lower sound pressure levels than if it had very little sound absorption, even if that wall assembly is preventing the same amount of sound from being transmitted through. But in any case, you get all these 1/3 octave band transmission loss values, and then you plot them against this curve, or you compare them. We plot them here so it's easy to see, but really the thing that you're interested in are the deficiencies between each 1/3 octave band and the contour. So here is the shape of that contour. And what you do is you shift this up and down. And when you want to keep shifting it up until the total of all the deficiencies equals 32 decibels, or 1 1/3 octave band reaches 8. If you reach either of those criteria, of either 8 in 1/3 octave band or 32 and all of them combined, then you need to step back 1. So that will end up being the limit right there. When you reach that criteria, you don't want to go past it. Let's say it that way instead of stepping back. So long as you satisfy that criteria that you're 8 or under or 32 or under, then whatever value this curve has at 500 hertz, that is your STC value. So if you had more transmission loss that was measured, this would get shifted up and you would get a higher STC rating. The calculations for all of this are actually fairly complicated. It's good to, it's nothing like too hard of math, but there's a lot of stuff that needs to work together. It's good to create a program that will do this for you. But here, this will essentially list what I just said. So you round the data to which the contour is to be fitted to the nearest integer. So all that transmission loss data gets rounded to the nearest integer. Then the values in table 1, so these values here would be for STC 0, because we have 0 at 500. At lower frequencies where we're less sensitive to the sound, it drops off. And then at the higher frequencies where we're more sensitive to the sound, it increases. But so values in table 1 equal STC 0. We derive other ratings by adding the same integer to all values in the table. So the goal, that might, hopefully what I said is a little bit clearer than that. I used a lot more words than was fit into this line here, but you want to look at all the deficiencies between that contour and your 1/3 octoband transmission loss data, and you want the sum of your deficiencies to be less than or equal to 32, or you want the maximum deficiency to be less than or equal to 8 decibels. And then wherever that line is, where this is still satisfied, the highest level where it's still satisfied, value of that shifted contour at 500 hertz will be your STC rating. An important thing to note is that this does not consider transmission loss below 125 hertz. This STC is focused on speech. It's for isolating speech between offices, between multifamily residential units. It's not a good metric to rely on if you're trying to isolate something that's low frequency but such as music or HVAC equipment. Example usages, if you have STC 50, that's what building code requires between multifamily housing units. STC 65 is more what you would want if it was between units of high-end condos, or the sky could maybe be the limit if you're trying to isolate some place where music's going to be performed, or movies with a something that's going to produce a lot of low frequency during the explosions, or if there's big mechanical equipment, then STC 65 or higher is what you'd like. There are a lot of variants of this, and that standard that I referenced, and I said I'll post the supplemental materials, it covers the field measurement version. So there's a laboratory measurement to get the STC, and then there's a field measurement to get the FSTC, so field sound transmission class. And we'll talk about these other ones down here too, but obviously we're starting with this FSTC. So a couple minor points about that. I mean, they're important points, but they're not the main bullet points on this page. So the first one is typically X minus 5 FSTC. So what we mean by that is that if you have an STC of 50 for the building code, then if you get 45 FSTC, that's acceptable. So the building code even says that in it. If you get 50 STC between multifamily housing, then your assembly should have a lab rating of 50 FS or 50 STC, and then if you have 45 in the field, it's okay. You meet the code minimum requirements. Next point, so sensitive compartmented information facility. These are SCIF rooms. I think our new research center, the defense one, that one, they have SCIF spaces in it. And a huge, major component of SCIF facilities is acoustical isolation, as you can imagine. If you want to compartmentalize a space where secure information is going to be discussed and you don't want to get out, acoustics is very likely one of the top priorities for that. So you need to, in that code, they require an FSTC. So it's a military, like a joint forces document. I forget the number of it, but it's joint forces something document, and it requires, there's two different classes of it, and FSTC 45 is required for one, and FSTC 50 is required for the other. I did a bunch of SCIF facilities for Raytheon once upon a time, and then I guess they got sick of paying me to do those for them, so they had me write a manual for them. So I wrote a manual for, they converted a lot of old spaces into SCIF facilities, and then they built a lot of new ones. So I wrote a manual of every possible condition you could think of that might come up that they, guidelines that they needed to follow to meet these two requirements. Next major bullet point, ASTC. So apparent sound transmission class. This is measured in the field. It includes flanking. We're going to define what flanking is here soon, but say you have, so one of the worst examples of this I ever saw was there. So it was a mega church built a youth building, and they had these different auditoriums on the top floor of this building. They had like the senior high room on one side, the junior high room on the other side, and so on. And they put like STC 70, 75 wall between the two spaces. But at the top, they just had a lightweight metal roof that spanned over both sides. And they, fired up one side, and you could hear it clear as day on the other side. And they're wondering, like, well, why did we get this? We put an STC 75 wall in between here. It was because of flanking. The sound goes up, it excites the roof structure, that lightweight metal roof. Just, it's like the old movies where train noise is heading down the train track and the robber puts his ear up against it. It's like that. The sound just traveled easily through that lightweight roof, and then the ceiling, the roof on the other side basically became a speaker that radiated out all that sound. So that flanked. It's like, like the military term, you're coming in around the side. It flanked the main partition. So you might have that through the ceiling, have it through the floor, any kind of other partition like that. So ASTC, it's a measure in the field. It's kind of like FSTC, but with FSTC, there's supposed to be an attempt to have eliminated flanking, or actually the code has recently changed to be, it used to be just based on FSTC, but now it's more based on ASTC. And usually you would just in the past say that FSTC is at least the ASTC, because that, so you'd want to get an ASTC that met the FSTC requirement, and you could say that the FSTC is going to be at least as good as the ASTC, because the ASTC includes flanking and the FSTC wouldn't. So I hope that made sense. I kind of said that quickly, but hopefully I said it clearly. You can rewind it and listen to it again if I went through it too quickly. The next one is the outdoor-indoor transmission class. So this one, remember we said the STC only goes down to 125. Well, this one goes down to 80 hertz. And the point of this is they realized another shortcoming of STC was, besides not attenuating music and movies and stuff like that with a lot of low frequency content, it also didn't attenuate traffic noise very well, because traffic noise has a lot of low frequency content. So this outdoor-indoor transmission class was developed. It's very similar to the STC. It just looks at lower frequencies. And a lot of environmental codes, like the LEED stuff, that will have OITC ratings as one of their possible solutions. Okay, so here we have a little bit more information about that flanking. I kind of described it pretty well, but here we have a schematic for it. So we have this unit here. The sound is generated here. The direct path would be this solid one. Flanking would be, it excites, maybe it's better to go this direction. This will be clear. So we have airborne, it's going up through the partition. This is, say, what you'd be testing the STC for. But the flanking excites the structure, and it passes up, and then it radiates out from the walls. Those would be the flanking paths. We see down here, flanking and direct, hashed and solid. Impact sound is mentioned here. There's a whole other side to all of this that is impact sound. Yeah, similar requirements. You need to have 50 IIC, so it's impact isolation class. You need to have 50 IIC by building code, or 45 IIC. That's just to meet building code. If it's market rate condos, then you'd go up 5 from there. If it's luxury, you'd go up 10 or more from there. So similar concept. This is just for people walking on the floors or jumping or dragging chairs or whatever people do. It's a measure of the isolation to the space below. You can have very different results for airborne and impact. Like, say you put a 6-inch concrete slab there, you get pretty good STC from that, but your IIC is going to be terrible. You'll get 50 or more with the 6-inch concrete slab. You'll get more like less than 25 on the impact side, and vice versa. You could do other, like if you put carpet on top, all of a sudden you're going to take your IIC from 25 up to 75, and it's not going to change the airborne whatsoever. We won't spend a whole lot of time on impact. Maybe that is about all I'm going to say about it right now. Maybe we'll bring it up again later. You should just be aware of that. This was from a project. It was a big mixed-use development in LA. Well, actually, there's sort of 2 different projects combined here. So some of this is from a report, and then some of this is from a previous project that was used in this report. So worked on both of them. This was a not student family. This was student housing in the United Kingdom, and they had so one thing. Our dorms don't really have this, but it's a fairly common thing in Europe to have a nightclub in your student housing, or at least a bar. All the student housing I lived in Denmark either had a bar in the building or it had its own building on the little student housing campus. But this one here, it had a sizable nightclub with 2 towers of student housing above it. And so if you notice here, the concrete here is like that's thick. I mean, here's, a floor. You say this is all in meters, but, this might be, say 4 meters, like 12 feet floor to floor. So, and here you have this concrete slab that's like half that. You almost have a 5-foot thick concrete slab. And then even over here, it's more like 18 inches. That's a fairly common construction type, the podium style, where you have like a mixed use level where everything's concrete and you have this really thick, like 18 inches or maybe more concrete level on the top. And then you build wood frame on top of that. But it had that at least 18 inches thick, maybe even 5-foot thick concrete at some places. The towers, they're directly overhead right here, but like this one's almost completely offset from being over the nightclub. This one is mostly offset from being over the nightclub. And on top of that, there's also a dropped ceiling down here. So you have dropped ceiling, something with some mass, few layers of drywall minimum, big air cavity, lots of concrete, and then these are offset. And still, there were, so like 10 decibels. So these dashed lines were what were considered acceptable. It's like meeting the building code. But here, this is 10 decibels above that. And in this case, I mean, they built this entire building. They thought they were doing a good job of isolation, and it's like incredibly loud. It's like it's twice as loud as it should be, and it goes up 1, 2, 3, 4, 5. There's still 5 floors that are above what the code or what's required. So my coworker worked on this one. I don't know, maybe it was like the peanut gallery on it or something, but he basically told them you essentially have to lift these towers up. You need to like lift up the towers and put them on springs. I mean, that's one solution. The other solution is to build this completely within its own box. That would likely be a better solution. Well, that would be a better solution from design, but at the point of where they would have to tear all this out, this entire nightclub, and then build it back in. He actually seriously thought that the easiest solution for them, and this just goes to show how bad all the possible solutions were to lift the towers on top of this building and put them back down on something resilient that was going to isolate them from this nightclub, which is ridiculous. But what else can you do? And just to show another example, I mean, this isn't an uncommon thing. Here's the Wynn in Vegas. I had heard lots of stories. I was putting this slide together for something a long time ago. I think I actually put this in a report. So back to this, we ended up using this. They were going to do a big mixed use development in LA, and they were going to have like a bowling alley, a nightclub, a movie theater. They're going to have all kinds of different things on the lower level. And when we showed them this and we showed them what kind of trouble they were going to have to go to, they decided just to go with mostly retail. And this, around that time, I knew that the Wynn had noise problems even on its top floors from the nightclub. So I went and looked, and sure enough, there was a review just from 5 days. This was just a random day, and 5 days prior to that, somebody had posted this. So they're staying on the 31st floor of the Wynn. And the nightclub is on, I think it's even below ground level. But, this wasn't like noise coming up shafts. It was the bass from the nightclub exciting the structure, and people, even up on the 31st floor or even higher, could clearly hear that, and it was bothersome to them. So big problem you gotta be aware of. Usually the best solution, it's not like that whole thing about putting a building on springs. It's not that crazy. Like concert halls, the entire building might be put on springs. Like if it's something downtown and there's a metro coming by, or there's just a lot of traffic noise all around, it's not uncommon for a building to be built on springs. So, the guy's recommendations weren't too crazy, but doing it to an existing building is pretty brutal. But that's one solution. If you're designing a new building, maybe you want to put it on springs. In this case, for that nightclub, if you're starting from design, it'd probably be better to build a box in a box. So here you have the structure of the building. And then here you have the space within which your movie theater, your nightclub, or whatever that's going to be loud is going to be located. You have the floor is isolated. So these ones are rubber, but you can get some that are spring. basically here, the ceilings have spring and neoprene hangers. The sides just have neoprene. The bottom has neoprene. Spring, all springs is a little bit better, but this is just a good conceptual image. This was a recording studio I did once for an art conservatory in San Jose, in the San Francisco Bay Area. But they wanted a recording studio, and they just had this space. And they're like, okay, we'll design this a recording studio. So this is the design I came up with. I think the next picture here shows, so we have, this is, the red box is all the structure. And then the tracking room, I forget, it's been a while since I did this one, but so we had the control and then ISO. I didn't remember if it was ISO and control or control and ISO. But so you have each one of these in their own box. And it's kind of like this one where the floor of each is floating, the walls are each. Ideally, you want an airspace, like you want no connection. And if you have to support it, you want to use something with neoprene or with a spring like this. And the ceilings were suspended. I have some more details here I'll show you on the next page, but 3 boxes within a box. This is how we isolated the floor in this case. You have these neoprene blocks and you have some fiberglass insulation that rolls out in between them. And a couple layers of plywood, kind of like a subfloor, and then add hardwood floors. Often it's good to have hardwood floors, and then you can roll out a thick rug with a pad underneath it. Maybe you can, if you just want to put them under the drum set or something like that, the things that are under the amps, the things that are noisier, you can, it gives you flexibility instead of just carpeting everything to begin with. Now, have some sections here through these walls to show you what they are. So most of them are like a double stud, airspace in between, a couple layers of gypsum board on each side. This one's different in that there's the exterior wall there. But the critical, it's easy to get a wall. Like, okay, we know this wall produces STC 70. I think it's probably close to 65. That one's more like 65 to 70, somewhere in there. Depends on how big your air gap is. But it's pretty easy just to get a wall that has a good STC rating and you think this will work. The devil is in the details though. Making all the floor ceiling terminations, like here we have all the floor terminations of these walls. Getting all of this right, and that's really the key to this. It takes a lot of attention to detail. The ceiling, we would hang a sound isolation ceiling, a couple layers of gypsum board on spring and neoprene hangers, and then we wanted an acoustical ceiling. So like a T-grid ceiling is good because you can, in one square, you can put sound absorption, in another square, you can put diffusion. You can mix and match those to whatever amount of diffusion and or sound absorption that you need. So having this sound isolation ceiling and then an acoustical ceiling down below, and also you might be hiding stuff in here. Like you want to minimize the penetrations through this. So if you have ductwork or some sprinklers or something like that you can run through there, that allows you to hide them. This was an interesting project. This was in Madison, Wisconsin, or just outside of it. Epic Systems. If you're ever in a doctor's office, I hope you're not there. I hope you're not there for coronavirus. But if you're ever in a doctor's office and you look over at the screen and it has all your medical records there, look, and there's a really high likelihood that it's Epic Systems. There's one other one that is fairly common too, but pretty much every time I've ever looked or every time I've asked any medical professional, they always say, yeah, we use Epic Systems. But so this is just one building on a huge campus. This room is underground for one thing. It's crazy. If you drove past this campus, you might not even know it's there. They have there's a big barn there. Like all their they it's a little eccentric, let's say that. But like this building here it has this Hobbit theme to it. And they named it Deep Space, but they have a bunch of stuff in there related to hobbits. But in any case, you're driving past the campus, you'll look over and you think this building is a big barn, but it's actually these really nice offices inside. And another thing with this company, they don't do the open office thing. It's a hugely popular thing right now. Everybody wants to have open everything. But these guys have every single person within the company has their own office, and they have all kinds of employees. But so one other interesting thing, just while we're talking about, they're completely net zero. They actually sell energy to the power grid in Madison. Like, with all their geothermal stuff, all their solar panels, they produce far more energy than they use. This building is underground. So it's incredibly insulated, both thermally and acoustically. It was so this room here, this was like phase A for it. And if I remember right, there are 15,000 seats there. And phase 2, there's infrastructure here to create a balcony. So they can build a balcony in here, and that would raise their seating to 25,000. So this is 25,000 seat auditorium underground, and it's basically for training. They train people how to use their software here. They have a lot of their big functions here and stuff like that. They use it for more than that, but primarily it's a training space. And so I mentioned how isolated it was being underground. For one, all the walls are thick concrete, and then you have multiple feet of earth on top of that. All the walls and the ceiling, it's all this concrete shell underground with a bunch of earth on top. And it was strange to be in there. So I was there through all. I was on the design team through all the design. And then under construction, I was there a number of times for construction administration, just meaning you go around and make sure that everything's being built as it should. And standing roughly where this picture was taken, it'd have all this kind of like earth moving stuff down here, and it looked like little kids' toys. Like this stage is massive. I can't remember how big this LED screen is, but it's something like, maybe I'm exaggerating, but it was like 75 feet tall, but like 100 and something wide. It's massive. There's like a 3-story building back here to support and cool this. It's kind of like scaffolding. There's a studio, multi-level studio back here too. But so one thing was just being here and seeing all those huge, they're huge pieces of equipment, but so far off and just looking like kids' toys. And being, so by saying that, I'm just trying to give the scale of this building. It was just huge. Like you felt like this little ant walking around in it. And if you were there after construction had stopped for the day, you would hear no noise whatsoever, just because the entire outside world is you're completely isolated from it. And it felt like you were in outer space. It felt like you're on a spaceship for some giants from another world. And they named it Deep Space. So I imagine I was probably not the only person that had that feeling there. They probably had that feeling when they were in there too and named it that. And then they kind of gave it a Hobbit theme on top of that. So Hobbits in space, I guess. But the main reason why I put this in here was because the mechanical system for this building was crazy. This drawing is just a PDF. So I had to analyze all of this. I mean, this looks like spaghetti to, this PDF was basically useless. I mean, it's a good image here to show you this, but getting in there and seeing it in 3D in Revit or AutoCAD also, I think we had Revit and AutoCAD models of this both in 3D. But some of these ducts, like here you can see the dimensions. I mean, this is like 66 by 60 something. So here you have ducts that are 5.5 feet wide. And here it looks just like thin spaghetti. Like the room where all this stuff was in was massive. You look up and you have like 3 levels of these ducts that are all 6.5 feet by 6.5 feet. Some of them are even bigger. Like here I'm seeing 74, so you like 8-foot wide ducts. I'm not joking that some of the ducts, like there was a lot of these came over and terminated in a corner here, or maybe it's somewhere around here. But they went down, and then there was a tunnel of ductwork that went underneath the seating, and they had underfloor supply, and you could literally drive a truck through some of that ductwork. It was just huge. But lot of equipment, mechanical equipment, and we wanted to make sure that this was not audible out here. We had all this great isolation. We didn't want to ruin it with the mechanical equipment. So we ended up essentially building well, more than 2, but everything on one side of the blue line, like over here is the seating area. All of this over here is almost its own building within all of this underground. There's an expansion joint between these 2 sides. So there are no rigid connections between the structure of this and the structure of this. So that helped us to still get the really low noise levels and eliminate the vibration like they wanted. I think I circled this because it was for a different presentation on a sort of different subject, but those are dedicated outdoor air systems. They just bring fresh air in. If you do this instead of just using packaged units for auditoriums, you can get a much more efficient system. Maybe I'm rambling. This is HVAC stuff. I think maybe I won't even talk about this. All I'll say here is a dedicated outdoor air system it can not only be much more energy efficient, but for an auditorium, it can also help a lot for bringing the noise levels down. Say like if you have a packaged system, so there's acoustical component to this, so I'll go into it. If you just use packaged units where, say, you're recirculating the air and you have the compressors, all the condensing units as part of that unit, the fans are in there, it's packaged. It's this thing that you put up on top of a roof, and it's designed for what a typical occupation might need. But an auditorium is different because you have so many people packed in, just tight together. And the latent and sensible heat loads are different for that. And it's different. So therefore, it's different than what a packaged unit is typically designed for. So if you instead supplemented it with dedicated outdoor air systems to get that fresh air and the circulation in without having to oversize the packaged units, you not only cut down on the noise because when you oversize those units, usually bigger means more noise. So by that, you're cutting down the noise. But then, like I also said, those bigger units also use more energy, and some of that's wasted. So this type of a system has acoustical and environmental or energy efficiency benefits. Here we just have some of the details. So this was the auditorium side. This was the mechanical unit side. So we had to make an expansion joint that was acoustically sealed, but there were no rigid connections between them. So not only horizontally, but also there's quite a bit of deflection. If you have this building and you bring 25,000 people in there, the live load it is going to drop the floors quite a bit. So we had to have all these sun isolation partitions that were flexible both vertically and horizontally. So we could keep the seal, and we could also stop the vibrations of the mechanical equipment from going side to side. This is just a general note. So it says pay attention to flanking paths. I gave that one example of that mega church's youth building. They so the main point here, sound isolation is only as strong as the weakest link. We're going to look at composite transmission loss soon. So you're going to see that you can have a great concrete wall, but you have one little crack in it or one little opening, or just like an unsealed door, it just completely destroys your transmission loss. So you really need to pay attention to the weakest links and deal with those, and don't forget about flanking when you're doing that. That's it for this one.